The last bit of information I want to talk about as far as sets are concerned is interval notation. So we often visualize real numbers on the number line, and frequently we'll need to describe an entire segment of the number line. One way to do that is to use set builder notation, which we talked about in the previous section. So for example, if we wanted to describe this set of numbers, right, all of the real numbers between -2 and 3, then we could describe it like this. We could describe it as a set of all x in R, where x is between -2 and 3, right? Pretty easy. Another slightly easier way to say the same thing is to use interval notation. Interval notation would describe that same segment this way. So it would use a square bracket and then -2, 3, and then another square bracket. And that, so in other words, these two sets are the same thing. This interval notation is just a slightly easier way to say what the set builder notation is saying. In fact, here are some common intervals that that we'll need to be able to describe. So if we wanted to describe all of the numbers between A and B, but not including the endpoints, then one way we could do that would be to use this set builder notation. A graph of this thing would look like this. So we would use open circles on A and B, and then graph the segment between them. In interval notation, those open circles correspond to parentheses. Okay, so whenever you use an open circle, you use a parenthesis. Okay. In fact, for that reason, sometimes people, when they're graphing these kinds of inequalities, instead of using open circles, they'll actually just use parentheses, right? I go back and forth sometimes on the notation that I use, but anyway, so that's that. If we wanted to describe all of the numbers between A and B, including the endpoints, well then when we graph it, we use closed circles. And the corresponding notation when we're using intervals is to use square brackets. So anytime you use a closed circle, you use a square bracket. And so again, for that reason, a lot of times people just put square brackets on these. Okay. And then you could have mixtures, right? You could have like an open circle on one side and a closed circle on the other. Right? So this denotes all of the numbers between A and B, including B, not including A, right? So in interval notation, we put a parenthesis where we had an open circle and a square bracket where we had a closed circle, a filled-in circle, okay? Same thing with the next one, right? The graph would look like this. And the interval would look like that. If you don't have like an upper bound, right? So if you're looking at all of the numbers bigger than A, then in interval notation, we would just use an infinity sign. We would say this is all the numbers between A and infinity, right? Not including A. If we want to include A, then of course we put a square bracket on the A. But with the infinity symbol, we always use a rounded parenthesis. Same thing if there's no lower bound, right? So if we're looking for all the numbers less than B, then we would say negative infinity to B. And again, not including the B, so we use a rounded parenthesis. If we wanted to include the B, then we would use a square bracket. And then if we just want to say all real numbers, the way to do that in interval notation is to say negative infinity to positive infinity. So this is how interval notation works. The graphs, I mean, that's what x greater than A looks like. This is what x greater than or equal to A looks like. X less than B. X less than or equal to B. And then finally, all real numbers. Right? So that's that. Right? Maybe we could label some real numbers down here, but but we're trying to describe all of them, so that's that. When you're writing something down in interval notation, it's important that the smallest number in your interval goes on the left and the largest goes on the right. So don't mix these up. So when we're dealing with like set builder notation or roster notation for sets, the order doesn't matter, right? But when you're dealing with interval notation, the order does matter, right? You've got to get this, the interval has to be arranged from smallest to largest. Okay. Okay. When using interval notation, so a few things to point out here, right? When using interval notation, we do not put braces around the intervals. An interval is already a set. So if we put braces around it, then we're talking about a set of sets, not a set of real numbers, okay? So this set right here, the set from 0 to 3, including 3 but not including 0, right? This interval, this is a set of real numbers. It's already a set. You don't need to put curly braces around it. It already denotes a set, okay? So this is the set of real numbers between 0 and 3, not including 0. If you put curly braces around it, now you're not talking about a set of real numbers. You're talking about a set of a set, right? A set composed of a set, where the set that makes up the set is the set 0, 3, right? Anyway, the moral of the story is don't put curly braces around intervals. You don't need to put curly braces around them. If you put curly braces around them, then your answer's wrong, okay? Because you're not talking about a set of real numbers anymore. Another thing that I'll point out, this messes students up a lot, but the interval from 1 to 3 is not the same thing as the set 1, 2, 3. There are lots of numbers in this interval that are not in this set. For example, 1.5 is in this interval. It's not in this set though, right? So it is true that the set 1, 2, 3 is a subset of the set of the interval from 1 to 3, but they're not the same set, not by a long shot. There are infinitely many numbers in this interval. In this set, there are only 3 numbers, okay? Another thing, just to point out the difference between these two sets, right? This one is the set of all numbers between 1 and 3, including 1 and 3. This is the set of all numbers between 1 and 3, including 3, but not including 1, right? So 1 is in this interval, but 1 is not in this interval. Any number slightly bigger than 1 is in this interval, just not 1 itself. So 1.1 is in the interval, 1.01 is in the interval, 1.000001 is in the interval, but 1 is not in the interval. Okay, similarly, 3 is in this interval, but it's not in this interval. Okay. Okay, and then like I said on the previous page, just one last thing to note is that when you write a set in interval notation, the order is important. The smaller number has to go on the left, the larger number has to go on the right. So the interval -1 to 5 means the set of all real numbers between -1 and 5. The interval from 5 to -1 is nonsense. It's nonsense. Okay. So don't write the numbers out of order. Put them in order from smallest to largest when you're writing down an interval. Okay, so with all that in mind, here's some practice. We're going to practice using some interval notation, doing some unions and intersections, right? So we talked about unions and intersections in 1.1, and then now in 1.3 we've talked about intervals. Let's see if we can throw those two concepts together. So I've got 4 different intervals here, and I want us to compute some unions and intersections. So I'll walk you through the first couple, and then I'll let you pause the video and see if you can do the other 4 on your own. Okay, but if I want to look at, you know, I1 union I2, so I1 is here, I2 is there, it's useful to draw a picture. So I'm going to draw a picture real quick. I1 goes from -2 to 3, I2 goes from -2 to 5. So I'm going to put -2, 3, and 5 on the map. I1 is going to be from -2 to 3, open circles in both places. I2 is going to be -2 to 5, closed circles in both places. So this is the picture that we're looking at for I1 and I2. Okay? So if I want to find the union of these two things, remember the union is the combination of the two things. It's all of the things put together. So if we put these two sets together, then that's the union of the two individual sets. And in this case, if I put both of these two things together, I'm just going to get I1, or sorry, I'm just going to get I2 back, right? Right? So my solution set is just going to be I2, right? -2 to 5. If, on the other hand, I'm looking at the intersection of these two sets, the intersection is where the sets overlap. So in this case, the sets overlap between -2 and 3, not including the -2 and the 3, right? So the intersection is just I1, as it turns out, right? So the intersection is I1. It's not always the case that when you're looking at the union and intersection of two sets that you're always going to get like one or the other. You could have a new set that's neither of the originals that you started with. So I'll let you work on the next 4. Go ahead and pause the video and see if you can work these ones out. Okay, here are my solutions. I'm only going to draw one picture for each set. So like C and D are comparing I2 and I4, and then E and F are comparing I1 and I4. So I'm not going to draw a separate picture for C and D. I'm just going to draw one picture for both of them. And so the picture would look like, excuse me, the picture would look like this. So I2 goes from -2 to 5. I4 goes from 4 to 7. So I'm going to put -2, 4, 5, and 7 on the map. And I2 is going to go from here to here. Closed circles on both ends. I4 is going to go from here to here. Open circles on both ends. Okay, so that's my picture. The union of these two things is going to be, it's going to go all the way from -2 and all the way up to 7, right? It's going to go all the way from -2 to 7. It's going to include the -2, but it's not going to include the 7. So it's going to go -2 to 7. The intersection, on the other hand, is just going to be where they overlap. They only overlap between 4 and 5. That's the only overlap. So between 4 and 5, not including the 4, but yes, including the 5. So the intersection is going to be 4 to 5. Okay, I1 and I4. Let's draw a picture. So I1 goes from -2 to 3, and I4 goes from 4 to 7. So I'm going to have -2, 3, 4, and 7. Here's I1, and here's I4. Right, this one is I1, this one is I4. So when I think about the union of these two sets, well, it's all of the numbers that are in either set, right? So it's the combination of these two sets. And in this case, since there's no overlap between the sets, I have this gap between 3 and 4. Here's how I write this down. So the answer is going to be -2 to 3. And then there's a gap, so I'm going to use the union symbol, 4 to 7. So there's the union of those two sets, right? The intersection, on the other hand, now this is where the two sets overlap, and there is no overlap. So the intersection is empty. Okay, so that's that. Hopefully that makes some sense to you. That's how intervals work. That's how unions and intersection of intervals work. Okay, here's some more practice. So let's see if we can simplify the following. We have negative 2 to 4 union z. Z is the set of all integers. That's an interesting set. So simplify the following. I mean, this is actually already simplified. I think this is about as simple as you can get. But maybe what I think I meant was like give the roster notation. So give roster notation. So so let's do that for part A. So I'm thinking negative 2 to 4, and then union z. So any integer is going to be in this set, but then also any real number between negative 2 and 4 is going to be in the set. So I think, well, goodness, how would I even do this? You can't really give the roster notation because there are infinitely many numbers. I mean, I guess ultimately what I'm trying to get you to see is that this set is going to look something like this. Okay, so the set's going to look something like this. First of all, any number between negative 2 and 4 is going to be in the set, not including the negative 2 and not including the 4, at least at first. Right? But then also any integer is going to be in the set. So negative 4 is an integer, it should be in the set. Negative 3 is an integer, it should be in the set. But nothing in between them should be in the set, right? Negative 2 is an integer, so it should be in the set. So I'm going to fill in that circle now. Negative 1 is an integer, so it should be in the set, but it's already been marked as part of the set. 0, 1, 2, 3, 4 should be in the set. 5 should be in the set, and so forth, right? Negative 5, negative 6, negative 7, 5, 6, 7. All of these things should be in the set. So you get this solid line between negative 2 and 4, and then you get these dots on all of the integers outside of negative 2 and 4. So that's kind of what the graph would look like. I guess there's not really a more simplified way to write this down other than the way that it's been written. That's the simplest way to write it. Okay, part B asks us for negative 2 for intersect z. Okay, we can do this one a little bit more easily, I think. So negative 2 for intersect z. So on the one hand, well, I'll do the same thing, right? Negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. Okay, so on the one hand, the interval goes from here to here. And then on the other hand, we have the integers, right? And we're looking for where these two sets overlap. Well, they definitely don't overlap at negative 3. They also don't overlap at negative 2, right? Negative 2 is in z, but it's not in this interval. However, they do overlap at negative 1. They overlap at negative 1, they overlap at 0, they overlap at 1, 2, 3. Then they don't overlap at 4, and they don't overlap anywhere else. So there's the roster notation for part B. Okay. Now I'm not going to draw a picture on every single one of these problems, but let's suffice it to say that C, so C is the interval from negative 2 to 4, this time including negative 2, and we want to take its union with Z. Well, this is the same as part A, right? Same as part A. It's exactly the same set. It's describing exactly the same set. Okay, you can draw the picture, but you're going to find that it's exactly the same as part A. The intersection, on the other hand, the intersection of negative 2 to 4, this time including the negative 2, is going to be really similar to this, but this time we get negative 2 in the mix as well, right? So because this set and this set both have negative 2 in common now, whereas this set and this set did not, right? Negative 2 was not a part of this interval. So we would get -2, -1, 0, 1, 2, 3. Stop at 3. -2, the interval from -2 to 4 intersected with the whole numbers. Now remember, the whole numbers are the positive whole positive whole numbers plus with 0 thrown into the mix. So they're not going to overlap at -2 or at -1, but they will overlap at 0, 1, 2, 3, and then they're also going to overlap at 4, right? Notice that 4 is part of this interval. So they're going to overlap at 4 as well. And then finally, -2 to 4, not including the endpoints, intersected with the natural numbers. Ooh, okay, so the natural numbers, those are the positive whole numbers, right? They start at 1, so it's 1, 2, 3, 4, 5. So they're not going to overlap at -2 or at -1. They're not going to overlap at 0, but they will overlap at 1. They'll overlap at 2. They'll overlap at 3. They're not going to overlap at 4 because 4 is not a part of the interval. So that's what that one would look like. Okay. Very good. Let's do another one. This is the last one, I think, before I introduce a new concept. So last one. Ooh, this looks interesting. So A is supposed to be this interval from -3 to 2, including the endpoints. And then B is supposed to be this weird set 5 over n, where n is an integer not equal to 0. Part A asks us for the smallest element of A intersect B. And part B asks us for the largest element of A intersect B, so smallest and largest. So I guess we should look at what A intersect B looks like. And in order to do that, I'm going to start off by figuring out what B looks like. So B is kind of an interesting set. Let's think about this. So for B, n is allowed to be any integer, just not 0. So I could plug in 1, for example. If I plug in 1, I get 5. If I plug in 2, I get 5 halves. If I plug in 3, I get 5 thirds, and then 5 fourths, and then 5 fifths, which equals 1. And then 5 sixths, 5 sevenths, and so forth. Notice that these numbers keep getting smaller and smaller. I started at 5. And then I got to 5 halves, which is like 2.5. Eventually I got down to 1. And now I'm less than 1, right? 5 sevenths is smaller than 1. So the larger my denominator gets, the smaller this number is getting. So this is getting closer and closer and closer to 0. Which leads me to believe that 5 is probably the largest element in B. It's probably the largest element in B. That's not necessarily the largest element in A intersect B, because notice that 5 isn't even part of the set A. But anyway, that's only if I'm plugging in positive numbers. I can plug in negative numbers as well. If I plug in negative numbers, so if I plug in -1, then I get -5. If I plug in -2, I get -5 halves, and then -5 thirds, -5 fourths, -5 fifths, which is -1, -5 sixths, -5 sevenths. Okay, so that's what the set B is looking like. So I'm thinking probably that -5 is the smallest element in B, because notice that these numbers keep getting larger and larger in the sense that they're getting closer and closer to 0, right? We started at -5, right? 0. We started at -5, and then we eventually got up to -1. And now we're at -5 sevenths, right? So we're getting closer and closer to 0. So I think -5 is the smallest element and +5 is the largest element in B. But that's not the question. The question is, what's the smallest and largest element of A intersect B? So let's think about A intersect B now. So A intersect B. So A is all of the real numbers between -3 and 2. And then B is this weird set that we just wrote out up here. So Obviously, the smallest element in A intersect B is not going to be -5 because -5 is not in this interval. Okay. If I go to the next smallest element, -5/2, that's like -2.5. -2.5 is within this interval. So I think the smallest element is going to be -5/2. And then, of course, the rest of these numbers are all going to be in there because these numbers are getting closer and closer to 0, but they're never going to get there, right? They're never going to get to 0. And this contains all of the real numbers between -3 and 2. So it contains, in particular, all of the numbers between -5/2 and 0. So these are all going to be in the intersection as well. So -5/2, -5/3, -5/4, and so forth. On the positive side of things, I think that, okay, so on the large end, 5 is too big. It's not in this interval. 5/2 is about 2.5. That's also too big. It's not in this interval. So that's not in the intersection, and that's not in the intersection. 5/3. 5/3 would be like 1 2/3. Well, not like 1 2/3. It is 1 2/3. But 1 2/3 is in the interval. So 5/3 is in the. So 5/3 is definitely in the intersection, right? And then so 5. I'm trying to get these in order. 5/3 would be in there. If I'm going from smallest to largest, I guess I should work from the other end of the scale. So 5/4 would be in there. 5/3 would be in there. So so maybe I would say 5/6, 1, 5/4, and then 5/3. And 5/3 is the largest element because 5/2 isn't in this interval, so it can't be in the intersection of the two sets. So so this is what A intersect B looks like. It's this weird set, okay? But this is like the roster notation for it, okay? So we can answer parts A and B pretty easily. What is the smallest element of A intersect B? It's -5/2. What's the largest element? It's 5/3. As n gets larger and larger, what happens to 5/n? 5/n goes to 0. It gets closer and closer to 0 as n gets larger and larger. So as n goes off to infinity, 5/n goes off to 0. Okay, part D, fill in the blank. A intersect B is the set of all numbers of the form 5/n where n is in Z and n is, okay. N is less than something or n is greater than something. So so I think we kind of figured this out up here, right? It's like n could be less than or equal to -2, right? Because -2, when we plugged in -2, we got -5/2, and that was in there. When we plugged in -3, we got -5/3, and that was in the intersection. When we plugged in -4, we got -5/4, and that was in the intersection. So I think n is allowed to be anything less than or equal to -2. It can't be bigger than that. N can't be -1, for example, because if n was -1, we would get -5, and -5 is not in the intersection. Okay. On the other hand, n could be, well, n could be 3, but n could also be 4 or 5 or 6, right? So it seems like n could be anything bigger than or equal to 3. Okay, it can't be smaller than 3. It can't be 2 because 5/2 is not in this intersection, right? So that's how we would fill in those blanks. Okay, very good. This one was a challenging problem for sure. If you had a hard time with this one, I mean, that's understandable. But remember, you can pause the video, you can rewind it, you can rewatch. So you may need to do that if you struggled with this one a little bit. I will kind of speak peace to your mind in saying that I'm not going to give you something this difficult on like a test or a quiz, but but it's a good exercise to make sure that you really understand interval notation, set builder notation, unions and intersections, and all of that stuff. Okay. Sometimes we're interested in the set of all real numbers except for a few. In those cases, there are several different ways that we can write down the set. So for example, let's say that we wanted to describe the set of all real numbers except for 0. So we could write that in set builder notation this way. We could say we're interested in the set of all x in R, right? Set of all real numbers except for 0, right? So the set of all x in R where x is not 0. Okay, so that's one way that we could describe that concept. Another way to describe the same concept is to use interval notation. We can say, well, I'm interested in all of the numbers between negative infinity and positive infinity except for 0, right? So I'm going to say I'm interested in the numbers between negative infinity to 0 and the numbers from 0 to infinity, just not 0 itself. So I've used rounded parentheses on the zeros in both locations, right? So that's how we would write it down in interval notation. Another way to describe this same sort of set is to use what's called set difference. So suppose that A and B are sets. The set difference of A and B is denoted by A minus B, and it's defined this way. A minus B is the set of all x in A where x is not in B. Okay? So A minus B it's like if you take out all of the elements in B, take all of the elements that are in B out of the set A, and then you get A minus B. That's what A minus B is. So it's like you're saying take A and then delete all of the elements in A that are part of B, and that's the set difference. Okay? So to describe the set of all real numbers except for 0 using set difference, we would just say, well, it's all of the real numbers minus 0, right? So you can see it's a really easy notation. Once you get the hang of it, once you get used to it, it's really a nice notation, right? It's really clear what this means. It means all of the real numbers except for 0. So a few examples here. This set is the set of all numbers between, well, it's the set of all real numbers except for 1, right? So rewriting that using set difference, we would say, okay, so this is the set of all reals except for 1. This set is the set of all reals except for, it looks like -2 has been skipped over, and then it looks like 3 has been skipped over. So I'm going to say this is the set of all reals except for -2 and 3. Okay. And this one looks like the set of all real numbers except for the chunk between -2 and 3. So I'm going to say, so this is the set of all real numbers except for the interval from -2 to 3. And you'll notice that I'm using square brackets here. That's because in this set, I don't want -2 to be included, and I don't want 3 to be included. If I don't want them to be included in this set, then that means they need to be among those numbers that I kick out, right? So I've got to include the -2 and 3 here in the numbers that I'm going to kick out of the reals in order to produce this set, right? So to give you just another example, I mean, if I wanted to do -infinity to -2, including the -2, union 3 to infinity, well then this, in using set difference, we would write this as R minus. This time I don't want to get rid of the -2, right? I don't want to get rid of the -2, but I do still want to get rid of the +3, right? So I'd write it that way. Okay, so that's how set difference works, and it's nice sometimes to be able to use set difference to describe certain sets. Let's go the other way around. Starting with set difference, let's see if we can write these in interval notation, and you'll get some appreciation, especially in part A, for why we like set difference in certain scenarios. Okay, Because in this scenario, we want to describe all of the real numbers except for -5, 0, 1, and 4. To do that in interval notation, we would have to write it like this. We would have to say, okay, this is -infinity to -5, skipping over the -5 to 0, skipping over the 0, skipping 1, and then 4 to infinity. So you can see it's a much longer thing to have to write out than this. This is much easier and much more clear, honestly. Because here, if you were just looking at this, it would be kind of hard to tell at first glance that, oh, that's all of the real numbers except for -5, 0, 1, and 4. But when you're looking at it this way, it's really clear that that's what you're looking at. So set difference is nice in a lot of situations. Part B. See if we can write this in interval notation. R minus 0 to 4. So all real numbers except for the interval from 0 to 4. So that would take us from -infinity to 0, not including the 0. And then we would skip over some, and then we would take it up again at 4 and go off to infinity, right? So this is all of the real numbers except for the numbers between 0 and 4, including 0 and 4. Same idea here. Here we would go from -infinity to 0, and then from 4 to infinity. And notice the use of parentheses and brackets, right? So here I want to describe all of the real numbers between 0 and 4, including 0. Or sorry, I want to describe all of the real numbers except for the numbers between 0 and 4. So this is all of the real numbers except for the numbers between 0 and 4. And here I was supposed to kick out 0, so I don't have 0 here. I wasn't supposed to kick out 4 though, so I still have 4 in the interval. Okay, so that's that. And then finally, set of real numbers except for the positive ones. Okay, so this would be -infinity to 0, like that. Okay, so that's it for interval notation and set difference. These things are going to come up again throughout the semester, and that'll do it for our discussion of sets. We're going to use sets all semester long, so I mean you're still going to see sets, but this is the last bit of material where I'm going to just talk exclusively about sets. We're going to move on to functions and linear equations and limits and stuff like that as we progress through the chapter. So I will see you in 1.4.